Well, now when we know what entropy is, we can learn the contemporary version of second law of thermodynamics, which says, well, which way actually processes in nature occur. And the second law of thermodynamics states that in any thermodynamic process which leads from one equilibrium state to another equilibrium state, the entropy of the system and its environment, well, since the processes take place in our universe, it means that the entropy, we can phrase this also as the entropy of the universe cannot decrease. I remember actually when Stephen Hawking was talking about entropy, and well, he pointed out something really very important. This statement tells us which way time flows. Do you see that? I mean, because with time, what happens with time, entropy of the universe grows, increases all the time. So if we have certain entropy today of the universe, tomorrow the entropy of the universe is going to be higher. It will increase, which means that after tomorrow cannot be like today. Why not? Because it would mean that the entropy would have to drop. Entropy gives the direction for time to flow, because time really says about the configuration of the universe. And well, if we look at the microscopic definition of entropy, what happens in the universe, it has to become more messy. It is becoming more and more messy, which I use as an argument with my wife. If she says that my room is too messy, I say that now it is impossible to clean this mess, because the only thing which you can do now with the mess in your room is to take that mess to a dumpster and mess up really that dumpster even more than your room was messed. All right. I want actually to take a break at this point and try to calculate entropies of various systems. It is that, well, increase in entropy, I mean, if entropy increases, it means that we cannot go back to the previous system or previous arrangement, which actually says that the process, if entropy increases, it means that the process which took place is irreversible. We cannot return to the previous state in the future. And why don't we try to calculate changes in entropy and try to avoid pitfalls? Well, yesterday, for example, well, we solved a problem for well, melting and freezing ice cube, or changing temperature of liquid. And I think that when we calculated that the change in entropy associated with heating or cooling a system, I mean, let's say water, was specific heat times mass of the substance, which changes the temperature, times logarithm of the final temperature minus initial temperature. All right, is that right? Just check it. Yeah, because I mean, I had to solve this problem in my head right now in order to recall the formula, right? So I think it's right. Anyway, if we look at that, well, this number is a positive number. This one is a positive number. If I cool a cup of coffee, Yeah, like how about if we take a look at this coffee over there? This coffee is losing heat energy, right? Its temperature drops. Well, according to this formula, if the final temperature, so after the class, the coffee will have lower temperature than at the beginning of the class, which means that this quotient is less than 1. Logarithm of a number less than 1 is negative, so I can see that this is less than 0. Well, it seems to me that it's wrong. It doesn't second law of thermodynamics say that the change in entropy should be well, not negative, that the entropy cannot decrease. Over here I have an evidence for decrease. Aha! System and its environment, correct. So, fact that cup of coffee decreased its entropy doesn't mean that the entropy of the universe didn't change. I mean, didn't increase. All right, so how about if I write here that this is coffee, and let's find out what is the change in entropy of the environment. Well, the environment is our atmosphere. All right, now let's find it out. What kind of process? I mean, atmosphere is, well, in principle, you should use almost, exactly the same formula, right? Now, over here, I will have specific heat of water and mass of water. I will have to use the same formula now for air. Actually, I don't even need to calculate that. Well, I can find out that the heat which was transferred from coffee to the atmosphere, well, this was a positive heat, right? So it's dq over, and here I will have temperature of the atmosphere, well, which will be that final temperature of the coffee. Now, when we calculated this one, how about if I think about just a differential amount of heat? Yeah, let's think about just a differential amount of heat. So change in entropy of coffee was differential heat which was transferred from the cup to the atmosphere. Well, we will have actually to do it in a reversible process, not in a real process. So we would have to think that we really cool off that coffee very slowly, which actually this process pretty much resembles it. Although precisely we would have to do it in such a way that the temperature, all the time we would have to cool off air, just let's say by 1 degree, wait until coffee drops to 1 degree. Then again, drop temperature of the environment by 1 degree and calculate entropy by 1 degree until it goes to that final temperature. This is how we would have to really imagine that the coffee is being cooled off when we calculate change in entropy, not like in this particular situation. Actually, I have a slide about this, and maybe I will even not go to that. I will just tell you what will happen. Well, over here we can recognize that change in entropy of the coffee is negative. However, change in entropy of the atmosphere, now that heat has to be delivered to the atmosphere. We will have to imagine again that heat is transferred in a quasi-static process to the atmosphere, but all the time we would have a lower value for the temperature when we for the air than for the coffee. So that quotient always is going to be greater for the atmosphere than for the coffee. So if we transfer certain amount of heat from coffee to the atmosphere, the coffee drops decreases its entropy, but air increases its entropy by a larger amount. So if I add those two numbers, I will get 0. All right. Now, I would like to emphasize that the heat which is taken in calculation of entropy has to be in a quasi-static process, not a real process. And I will give you an example of a trap which actually I swallowed. I mean, it is that when I was a student, I made this mistake. I thought, well, how about if we think a process in which let's say I have a container, sealed container with vacuum, and over there is a balloon with a relatively strong surface, so it's a Mylar balloon, so that it, despite it is vacuum over here, it is confined. And suddenly the balloon breaks. And this air fills up the entire volume. So let's say that we had n moles of gas over here, and of a particular gas, so it will have a particular molar heat capacity. If it were a monoatomic gas, like, oh yeah, if it was helium, actually it's a monoatomic gas, so molar heat capacity will be 3/2 times gas constant. Now, when it breaks, it fills up that volume. And, well, to me, well, it was a free expansion. Really, this was an example of free expansion. So how much work does the gas perform? Think about this. How much work does the gas perform? Actually, it's not a quasi-static process. This is not a quasi-static process. Now, before actually you figure out how much work the gas performs, think about on what? There is nothing on which the gas can perform work. Recall that this PDV was work done on the walls, on the piston, right? Over here we don't have a piston, so when it expands, there is no work done by gas on anything. This is why it is called free expansion. Actually, there's one more argument for that word free. Figure out how much heat was delivered to the gas. And from what? Nothing, right? So there was no heat delivered. In free expansion, gas does not interact with anything. It means that no work is done by the gas, and no heat is delivered to the gas. Well, when I was a student, I figured out, well, so if there's no heat delivered to the gas, obviously change in entropy of the gas is how much? 0, right? This is what I figured out. Must be 0 because heat was not delivered to the system. But on the other hand, I knew that when entropy doesn't increase, it means that the process is reversible, so that in principle the system spontaneously is supposed to come back to the previous state. And I thought, well, obviously it won't compress on itself on its own. So to me, that process was not, I didn't see how to reverse, so I thought, well, entropy should increase. So I had two conclusions. And the reason for the mistake was that I evaluated entropy improperly. I evaluated entropy using the real process rather than quasi-static process. So what we have to calculate now is to find out how much, by how much entropy of that system changed if we choose a process from initial state to the final state, which is a quasi-static process. How about if I actually mark the two states? So we have certain volume, certain pressure. when the gas was compressed, it had low volume. Let's call this point A. It had low volume and relatively high pressure. When the balloon bursts, after balloon bursts, volume increases, pressure drops. Yeah, let's call this state C. Now, what happened, by the way, with temperature of the gas? Let's try to find out what happened. Yeah, because now we have to figure out not a real process, but we have to imagine a slow process leading from one state to another state, a quasi-static process. We can choose one of those, I mean, slow heating, in which the heat delivered is always proportional to the differential heat delivered is always proportional to the differential change in temperature. We can use adiabatic process, in which entropy doesn't change at all because indeed over there heat is not delivered. We can use isothermal process, isobaric process, isochoric process, or combination of them to find out how much entropy would change if the process was quasi-static. And then from the definition of entropy we will know that this was change in entropy in any process, because it does not depend, change in entropy depends only on initial state and final state, does not depend on the process. Actually, it's a very good choice, although later I want to show you if I don't another. There is a good reason, which is isothermal process. And state. Yes, so free expansion, heat delivered in that free expansion was wrong heat because it was not a quasi-static process. However, isothermal process was quasi-static process, and combination of isobaric and isochoric process were also isothermal process. Actually, as an exercise, I suggest that now you try to do it on your own. How about if we consider this process? Try to figure out by how much what is the change in entropy if you calculate it using first isochoric process and then isochoric process and then isobaric process. This is a different process. You change the order. Let's find out go ahead and find out what will be the change in entropy of that gas in such a process. So this will be all for today. Thank you very much and see you tomorrow.